Topic 3.3 is over zeros of polynomial functions. We're going to talk first about multiple zeros of a polynomial function. So if you have, let's say, a polynomial that had a factor, more than once, when we, in the past, if we had like a binomial to the third power or something, or a binomial squared. So that means it was a factor either 3 times or 2 times. And so that's where we're going to talk about multiplicity of a factor. And then below that, it says number of zeros of a polynomial function. So a polynomial function has so many zeros where each zero has a multiplicity. So all that means is, like, if you look right here, total number of zeros this has is 2 plus 3 plus 1, so 6 total zeros. But some of them repeat, okay? And so if we were to find the zeros of this polynomial function, for instance, we're going to say the x minus 5 factor that was squared, the zero for it, you just take x minus 5, set it equal to 0, and we know that to zero that out, x would have to be a positive 5, right? Because you would add 5 over to zero that out. So the zero of that factor is a 5. That factor has a multiplicity of 2. That means it was a factor twice. So that's what that's meaning. Find the zeros, which we found. This is the 0. This is what would zero that out. And state the multiplicity, which would be 2 times. And in web design, there'll be like a drop down, and you'll get to drop down here, and you'll choose a number. So x plus 2 to the third power. So if I were to see what would zero that out, I would have to subtract 2. So x would end up being a negative 2. So the zero of that factor is negative 2. And it has a multiplicity of 3. And then x plus 4 is a factor. You don't see an exponent for that one. So it's going to have an understood one. You don't see them, but just remember that there is like an understood one there. So this 0 would be a negative 4 because, again, you subtract to move that over. So this one has a multiplicity of 1. So that, so negative 4 can only factor out of that 1 time. So the difference between actual zeros and possible zeros, which is what we're going to learn about first, is when we talk about the rational zero theorem, we need to get a list of numbers that we could at least try. It's like a target. Okay, so they're possible, they're not actual zeros that always zero out the function. When you look at all this, it's kind of some busy work here. I like to get my highlighter out. And if you look at this, these 2 things right here, we're going to be focusing on that. So it says P is an integer factor of the constant. And that just means whatever that last term is. In this case, it's that a sub 0. But it's the constant of the polynomial. And Q is going to be like the leading coefficient. Up here, it's shown as like the a sub n. Really fancy way to just say whatever number's in front of the first term is going to represent the Q part of what we're about to learn. And then whatever your constant is going to represent the P. So to list all the possible rational zeros, we're going to put your P's over your Q's is what I always say. So in this case, if we're listing all possible rational zeros, we're going to put our P's over our Q's. So my P is the constant, so it's 18, and my Q in this case is a 4. And so what we'll do to list all the possible zeros is we're going to list every factor at 18, meaning all the things that can go into 18. So 1, 2, and I'm putting plus or minus because I could divide by a positive or a negative form. We could divide by 3, 6, not 7, not 8, but 9, and then nothing until 18. And some people will just put plus or minus over here and just know that all the positive and negative forms apply to those numbers. And then for 4, we're gonna list what would, plus or minus 1, what would go into 4, plus or minus 2, and plus or minus 4. So what you're gonna do is you're gonna generate a list from that. It looks kind of weird right now, but basically all of these numbers could be put over 1, they could all be put over 2, and they could all be put over 4, so there's quite a lot of numbers. So let's show the over 1s is the best way that I describe it. So we can have a positive or a negative 1, 2, 3, 6, 9, and 18. And you don't need to put them actually over 1 because that's an understood value, right? So those are the over 1s. Now let's do over 2. So we're going to do plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 6 over 2, plus or minus 9 over 2, and plus or minus 18 over 2. But then you're going to want to go back and simplify. And sometimes one of these numbers, when you simplify, appears in the list before, like 2 over 2 reduces to 1. So that's kind of a repeating number. So you're going to exit out. 3 over 2 is a new number. 6 divided by 2 is 3, so that would be like a repeating number. 18 divided by 2 would be 6, so that's repeating. So in the over 2 list, you just have 3 more options. And then we have an over 4. So plus or minus 1 over 4, the comment, plus or minus 2 over 4, plus or minus 3 over 4, plus or minus 6 over 4, plus or minus 9 over 4, and plus or minus 18 over 4. This plus or minus is get messy, so like I said, if you don't want to write, I mean, have to, but. And then again, reduce. 1 over 4 is new, but 2 over 4 would reduce to 1/2, so that's repeating. 3 over 4 is new. This would be reduced to 3 over 2, which is in that previous list, so that's repeating. 9 over 4 can't reduce, it's new. 18 over 4 reduces to 9 over 2, which is actually a repeating number. And so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's technically 24 possible zeros in this list. And so in WebAssign, if you had one like this, I tried to pick ones that weren't really long typing in numbers, but if you had one like this, you would have to go type in all the positive values with commas and then all the negative values, all the positive values, and all the negative values of those fractions. So you would have 24 different numbers to enter into WebAssign. So doing another one, listing the possible rational zeros. Again, this is just a list that you can choose from to see if it is a real zero once we get to learning if they're actual zeros or not. And this is by putting our P's over our Q's. So our 15 over our 6 in this case. So a positive and a negative 1. 2 can't go into it, but 3 can. 5 and 15 are all the numbers that can go into 15. 6, we actually have kind of a few. We have 1, 2, 3, and 6. So from here, I like to just, for me, I organize it by the denominator, I guess. So I'm going to put them all over 1 to start with. So we'd have 1, 3, 5, and 15. If I put them over 2, I would put 1 over 2, 3 over 2, 5 over 2, and 15 over 2. And I'm just really in the habit of always writing plus or minus. Over 3s, none of those reduced, so they're all new possible zeros. So far we have 8, actually 16 in our list, right? So plus or minus 5, or I don't know where I was getting, I just jump into 5. 1 over 3, plus or minus 3 over 3, plus or minus 5 over 3, and plus or minus 15 over 3. And a couple of those do reduce. 3 over 3 is 1, which is there, so that's a repeater. 3 goes into 15 5 times, so that's a repeater. And then we can do over 6. So plus or minus 1 over 6, plus or minus 3 over 6, plus or minus 5 over 6, and 15 over 6. 1 over 6 doesn't reduce, but 3 over 6 does, so 1/2. Which was in that list above, so that's a repeater. And then 15 over 6 reduces to 5/3, which was in this list. These others don't. So we have 8, 9, 10, 11, 12. Again, we had 24 total possible zeros. We're going to be learning how to find the actual zeros later, but this is just one step of leading us in the direction of finding the actual zeros. And it just gives you numbers that you can choose from that have, like value or would make sense to even try. Even though there's a lot of them, at least it's not an infinite number of possibilities. Another thing that we learn how to kind of like, narrow down whatever it is that we're going to try when finding our real zero is the Descartes rule of signs. This is just another way to obtain some information about the zeros you're going to have. And so this rule tells you the number of positive and negative zeros in a polynomial. One thing is we're going to be counting sign changes from term to term. And so I'm using the same polynomial for this one, if you notice, to find the positive zeros and the negative zeros. And so we're going to be counting sign changes. And the thing is, if you can subtract however many sign changes there are by 2, you will, because we could say that there's 0 or 2 possible positive zeros, okay? And that's what it means here by the number of positive real zeros of P is equal to the number of variations in sign. That means the changes of the signs of P of X, or that number decreased by an even integer. Okay, so that just means if you can subtract it by 2, then you should subtract it by 2 until you can't anymore. So let's just apply this. So here, I see I'm going from a positive to negative, so that is one sign change, but negative to negative isn't. Negative to positive is a second sign change. Positive to positive, positive to negative is a third sign change. So there are 3 sign changes. So we can say there are 3. And since we can subtract 2 from that, an even integer, you're going to always at least try that. If it's the number 1, you can't. If you can subtract 3 from that, 3 minus 2 is 1. So what we would say is there are 3 or 1 positive zeros. So it kind of gives you a range or an idea of how many of the zeros might be positive. So like from that list, maybe you'll choose positive options instead of trying to choose negative options when you go try to find the actual zeros. Now your negative zeros, you can make this as complex as you want, but basically in these instructions, it's saying you're going to change all the x's to negative, then simplify. But if you think about, if I change negative, if I change that the x is raised to the 5th power to a negative, that's going to stay negative, right? But if I change, or it's going to become negative rather, if I were to change negative x to the 4th, that stays positive. So really the easiest way for me to describe this is to just go change all the odd exponent signs. It's the fastest and the easiest way to explain it, that if this is a positive, just like I said here, if I change that to a negative, all of these, you could go in there and change to a negative, change that to a negative, and that means the whole term would end up just changing its sign. The even integers stay the same because that would end up just being a positive, keeping that a negative 3x to the 4th. So we're just going to go change all the odd exponent terms sign to whatever their opposites are. And if you really want to see that at work, I will kind of write it out a little bit more here for you to see on each one of them. Don't generally do this, but I'm going to now. So negative x to the 4th. So if you take each one of these, change those x's to negative, and you So I won't do it like this in the future for sure, because it's just super time consuming unless you can just remember to change all the odd exponent terms to a negative. Okay, so if I were to look at this, that means negative x to the fifth power. That would make this a negative number. So a positive times a negative makes that now negative 2x to the fifth. So that's why we changed that odd exponent. But negative times a negative times a negative times a negative makes that x now positive. So it's still just a negative 3x to the fourth. So this sign didn't affect or change the sign like this one did. This changed it to a negative because of the odd exponent. This one would be a negative times a negative times a negative. So it'd be a negative x to the third. So a negative times a negative makes it a positive 19x to the third. Positive, or this one is a negative times a negative would make that a positive x squared. So we didn't change the even exponent term. A positive times a negative makes that a negative 35x. So again, it just kind of shows that we were only changing all the odd exponent terms sign. Real easy way. And then you go count your sign changes. So negative to negative, not a change, but here to here is one change. Here to here is a second change. So there's 2, and since we can subtract 2 from 2, and we actually get a number that's not a negative number, that means we would say there are 2 or 0 negative zeros. So if you're looking at those possibilities, this is just a possibility, it's just information you gather. It looks like there could be more possible positive zeros. So I'd probably venture or try positive zeros before I would plug in some negative zeros. So now we're going to actually do it. And for the sake of time, I don't always try some and them not work just because it's just time consuming to do that. This is time consuming to find actual zeros. But we're going to go through some steps through all of these to find the actual zeros. So these actual zeros would be like factors of a polynomial. We're just going about it in a different way because we can't really go factor this polynomial. And so we do it really by using synthetic division. So the first thing that we'll do is just gather some information. It's always good to determine the degree, meaning like how many zeros are there going to be. So like in this one, I know there's going to be 4 zeros, right? Because that's the biggest exponent. The second thing is you would want to go apply Descartes rules of signs. I know some people might skip over it, but you do need to understand this process a little bit, if anything, for questions on the test. So I would go count sign changes. So from here to here is 1, 2, and 3. So for our positive zeros, since there's 3 and we can subtract 2 from that, that means there's 3 or 1. The negative, we would go change all the odd exponent signs, then count their sign changes. So that'd be like a 4x to the fourth. But then we would have, I'm going to go ahead and write this down the way it's given instead of changing it as we go. How about that? So we would have a positive here and a negative here. So the odd exponents, 3 is an odd number, 1 is an odd number, and then count sign changes. So positive to positive, positive to positive. So no sign changes so far until we get here. Positive to negative, there's 1 sign change, and negative to negative. So for negative, there's just 1 possible negative 0. So that's kind of answering the Descartes rule of signs. If I'm honest, just me as a doing it myself, it's not a big thing that helps me pick the right numbers always to use and try. But really, the big thing here, I'm gonna renumber this one, is check those suspects. That would be your P's over your Q's. Doing your P's over your Q's is the biggest part because it gives you numbers to try from. And so remember, in this case, my P is a 9 and my Q is a 4. So we can have 1s, 3s, and 9s in the top, 1s, 2s, and 4s. And I did kind of simplify my positive and negatives because I think we've talked about that quite a bit in and out, that all of these can be positive and negative forms. So for my P's over my Q's, I have over 1s. I'm going to have 1, 3, and 9. So the positive and negative form of all of those. And then I would put those over 2. So 1 over 2. Out of habit, I think I did my positive and negative sign. 3 over 2 and 9 over 2. And then now we're putting them over 4. So our positive and negatives, 1 over 4. 3 over 4 and 9 over 4. None of those repeated. They were all different. None of them could reduce. So we had 9, 18, because the positive and negative forms of all of those that can be options. So what we do is then we just go work and try to reduce the polynomial, meaning we're going to go try to do synthetic division until we get down to just 3 numbers left over. When we get 3 numbers left over, we can just factor that quadratic equation and then find the last 2. So for instance, let's just go through those steps. We have counting down 4, 3, 2, 1, and none. We're not missing an exponent. So we're just going to have 4, negative 16, 7, 18, and negative 9. And this is where you're picking a number from this list over here. Because I've already done it, I'm not going to start with 1. 1 is not a factor or a 0. And I'd like to go with positive ones just because I know there's more possible positive than negative. So I would probably then move on to 3. If I tried 1 and it didn't work, I would honestly probably also try negative 1. Positive and negative form, even though I said there's more positives, but you can try any number you really want from this list, however you want to do it. So I'm going to use 3 because I know 3 works. 3 times 4 is 12, and that's a negative 4. 3 times negative 4 is a negative 12. So 7 minus 12 is negative 5. This is a negative 15, which gives us a positive 3, and that's a 9. So remember, we know it's a 0 because it zeroes out. If you would have tried a positive 1, you would have gotten a remainder, so it's not a 0 of that polynomial. So then from there, I would repeat. We would take that and try, sometimes you can try 3 again if you want. I know that 3 doesn't work. I know probably the easiest one to do now is negative 1, which really I probably would have tried if after 1, positive 1 didn't work if I did that. So negative 1 times 4 is a negative 4. Combining that is negative 8. And then positive 8, 3, negative 3, and 0. So once you get down to 3 numbers, we can turn that into a quadratic equation. So remember, this would mean this is a 4x squared minus 8x plus 3. And so from here, it would be quicker, more efficient if you can factor to solve for the last 2 zeros. So this would be a slide and divide problem. We'd have to slide 4 to the back and multiply to have x squared minus 8x plus 12. If I take 2 times 6, and if they're both negative, they would add up to be that negative 8. We got x minus 2, x minus 6, and then divide by 4 to put that 4 back in it. Remember, this would be like saying x minus 1/2. Because you want to reduce that, and x minus 3/2. But then you'd want to set those factors equal to 0 and solve, like get the x by itself. You don't really have to pull it back up in front because the purpose is not to leave it in factored form, right? We're just trying to get x by itself. You're welcome to pull it up. You're just causing yourself an extra step, which is fine when you're solving for x. I guess I better push that up so you can see it. So the zeros that we found for this polynomial, remember we're supposed to have 4. So x could be 3, x could be a -1, 1/2, and 3/2. So sometimes, when you're going through synthetic division, you can go towards the fractions and try them. I would say as a whole, most of the time, we always use whole numbers to try it. Sometimes veer from fractions, makes our brains think. Okay, let's turn the page. All right, so let's do another one. And actually, I'm going to skip this one and go to this last page. I'll have the solutions of this one done just for video purposes. I'll be doing 2 of them, and then you can try this one and check the solutions in Blackboard under the completed notes so you can see the solutions for that one. So I'm going to do this one. It's just a little bit quicker and makes this video not quite as long. So I know there's going to be 4 zeros. Sign changes. Like I said, I know this isn't always the best indicator. Best indicator is definitely your P's over your Q's, but it's good to know how to use Descartes. But we have 1 sign change only for the positive zeros. For the negative, just going to use the color pen even up here. So this would be a negative, and this one would be a positive, right? I'll have to ignore the orange when we go back and start working with it, but we would be going from positive to negative, so that's 1 change, and then negative to positive, that's 2 changes, and positive to negative, that's 3. And so since we can subtract 2 from that, we would say 3 or 1. So you would probably assume that there's going to be 3 negative and 1 positive. And that's not always the case, but it does work out a lot since there's 4 zeros, right? So I would probably try negative factors before I started with positive factors from my P's over my Q's. And what's great about this one is my Q is a 2 or my P is a 2, and my Q is a 1. So we just have plus or minus 1 and 2 as possibilities to use. Kind of getting down to the beef of it with a pretty easy example. We're just going to start doing our synthetic division. So we have 1. This is a positive 1 as well. This was a -3. It was actually a -5 before I changed it with orange, and a -2. So I would start with -1. Number 1 is the smallest number. Number 2, it is a negative. -1 times 1 is -1. -1 times 0 is 0. -1 times -3 is 3. -1 times -2 is 2. Remember, you can repeat them too, especially when you don't have many options. I would try -1 again because it can be a factor more than once, as we started out today with the multiplicity thing. So we're going to bring that 1 down. -1 times 1 is -1. +1 and 2. And then from here, you have your polynomial. So this would be an x squared, a minus x, and a -2. You want to put those ones in front of it, you're welcome to do that. So remember, we're solving for those x's with our quadratic equation. So if I had an x -2 and an x + 1, using opposite signs, 2 times 1 is 2, -2, +1 would make that -1 middle term. Set each of those factors equal to 0 and solve. So x could be a 2 or a -1. So it looks like, x could have been -1 3 times. Just like that. So these problems can be time consuming, like I said. You may have to have extra paper or a pencil so you can erase, because there's going to be times you're going to plug something in and it's not going to work. For example, if I had tried, would like to do at least 1. If I had thought, well, I'm going to try +1. before I actually did the problem. We know that that is not a zero because of the remainder, right? And so I went straight to the factors just for instructional purposes, but we know +1 was not a zero for that polynomial. And so kind of back on that last one that I did skip over, I would say at this point, you go try it. You check your solutions. I'll get you started on it, and then you check your solutions on it. There are 4 zeros in this one. Descartes rule of signs. There's 1 change, 2 changes, 3 changes. So for the positive, there are 3 or 1. And for the negative, right, the sign changes underneath this sign. This would be a positive, and this is a negative. So positive to positive, positive to negative is 1. Negative to negative, negative to negative. So just 1 possible negative. And then you would try your zeros, your p's over your q's. So 4 over 3. So we have 1, 2, and 4. And 1 and 3. So we have positive and negative 1, 2, 4, and then we need to put those over 3. Positive and negative 1 over 3, positive and negative 2 over 3, and 4 over 3. So 12 different options. So then you would set this up: 3, -4, -11, 16, -4. I don't have this one completed right now. That's why I was tempted to not do it with you, but I think I'm going to go ahead and just give it a try. So 1 times 3 is 3, which is a -1. -1 makes that a -12. -12. And that's a 4. And so we did it. We found one of the 4 zeros. So let's see if we could try that again. I feel like we may not have great luck with 1 again, but I'm going to do it anyways. So 1 and 3, 2, yeah, so it's not going to work, is it? We could try -1. So let's see what that does with it. This is exactly what I would do if I were doing it on my own. So it'd be a -3, which makes that a -4. And that makes that a +4. Negative times a negative is 4. And then that would make that a -8. So yeah, that didn't work again. So then I would go to 2. And that's where it gets kind of messy and you may have to rewrite. So we have 3, -1, -12, and 4. Actually on this one, as I sit back and look at it, you could factor this by grouping and it would be quicker instead of waiting to get down to 3 numbers. And so I'm actually, you can, but if we factored this, if we turn that into 3x to the third minus 1x squared minus 12x plus 4, because remember, we can factor to get our polynomials to find the rest of the zeros, and we know how to factor by grouping. So don't forget that you know how to factor by grouping. And I think that's why I put this one in the notes, which I'm glad that we're going ahead and doing it together. So this is a group and this is a group. So I could factor out an x squared, which would leave me with a 3x minus 1. And here I could factor out a -4, which would leave me with a 3x minus 1. So you need to write that underneath there to see that division. Do that. So remember, the whole purpose in factoring by grouping is to get matching parentheses. And you put those together. And that would be a quicker way in one like this. If you kind of take a look at the numbers, when I looked at it, I was just kind of seeing that relationship that I could maybe factor by grouping. So if you get down to 4 and it's kind of hard, you may just check. Look and see if you think you could split them into groups and factor. So 3x minus 1 equals 0, x squared minus 4 equals 0, and we can go find the other 3 zeros from here. So we would be adding 1 and dividing by 3 to get 1/3. You know, you would have had to try out the 1/3 in the list over here, which is not a number that we generally will hover towards. Here we would add 4 over and then take the square root. So we could get x equals 2 or -2. So we probably would have worked it out if we would have just kept going on this step. If you don't really like the factoring by grouping, that may have been what you did. So, but just remember, you're not limited to only factoring trinomials. You can factor 4 terms if you remember, if it works by the factoring by grouping. So one of our zeros was a 1, and then the other 2 we found by factoring was a 1/3, a 2, and a -2. If you hate grouping, you may have just spent a little time like I almost did, and you would have still found the same ones. You just would have gotten down to a trinomial that would have had a factor of these other 2 left over.